Welcome to part 3 of our electromagnetic induction, and we're going to talk about two examples or two applications of electromagnetic induction. We're going to talk about electric generators, and we're also going to talk about transmission lines. Here's a picture of an electric generator, and we can see that we have like a spinning axle here. It's rotated mechanically, so something's rotating this. Like you might think that maybe there's a paddle wheel on here, and this is connected to a dam, and the water going over the dam is making the paddle wheel rotate, which is creating the rotation here that we see. And we can see that this cylinder is being rotated in a magnetic field that's created by the north face of this magnet and the south face of this magnet. So it would have magnetic field lines going from north to south. And so there's a coil inside here. We can also see that we have one of these. These are usually brushes. So a brush coming off here going to our light and another brush here going to our light. And when this turns, the electricity would be generated and create this, causes the light bulb to light up. And this would be like what it looks like inside. We can see that we have the magnetic field lines, and then this coil of wire is turned around this axis, and so it's moving around like this, and that we can see that there's going to be a flux change, right? Where it's going to become a maximum, and then when it's parallel to the field lines, it's going to become a minimum, and it's going to keep rotating around. We also can see the equation for the EMF. So an induced EMF or induced voltage is given by the number of turns, or the number of loops that we have, times the magnetic field, times the frequency here, times the area of the loop, and then times sine omega t. So the sine omega t is the thing that allows this to change. So this is representing the change of it going fully in the field to not in the field at all, and then fully in the field and not in the field. So you can think about drawing a sine wave, and that would help you to understand how the changing value for the EMF. Here's another example. You can kind of see it a little bit better how this loop is going to be rotating. So something's causing it to rotate. You can see the brushes here and how the top part of the wire is connected to this brush, and then the bottom part of this wire goes through the brush and goes to the next one. And so the current that's created here can go through this now circuit, and the voltage would be used in the circuit. We can also see the sine wave here that we see from the equation for the EMF. When we take the derivative of the flux, we know the flux is B, the magnetic field, times the area, times cosine omega t. And so if we want to take the derivative of that, where everything is constant, the A and the B, and the cosine omega t isn't a constant with respect to time. So that's what we're going to be integrating. And that's where the omega, because we have to take the derivative, we're taking the derivative. We have to take the derivative of the argument of the cosine, and that's where the omega comes from. And the derivative of cosine gives us a negative sign. And then we do that for every loop. So usually in an electric generator, this shows just one loop so you can see it, but there's usually hundreds to thousands of loops in there, and that's where the n comes in the equation. Now let's talk about transformers. So a transformer is something that is used at your home, or it could be up the street from your home. And what happens is you have a high voltage line that goes into a transformer, and the transformer usually steps that voltage down to voltage that we use in our homes. And so we have a primary coil, which has the high voltage, and then a secondary coil, which typically has a lower voltage. The way this works is if I have a current coming through and going through these loops, and these loops are wrapped around this piece of laminated iron core, there's a current that's driven in this loop, and that driven current creates a magnetic field, and it's AC current. So AC current creates a changing magnetic field, or changing current creates a changing magnetic field in it. So it's going to create a changing magnetic field in this laminated core, which gets transferred, through the laminated core over to the secondary coil. So the secondary coil has a changing magnetic field, and that creates an induced current in my secondary coil, and that's what is sent to your house. And so the way you figure out what the voltage would be is you can use this formula. So the potential of the secondary coil divided by the voltage of the primary coil is equal to the number of turns in the secondary coil divided by the number of turns in the primary coil. And so usually, like you can see in this picture, we have a bigger number of coils in the secondary coil. So this number is going to be bigger than the number of coils in the primary. And so that tells me that if this number is bigger than this number, then that tells me my my source is going to be bigger than my primary here as well. So these are directly connected. So if I wanted to calculate what the V secondary is, I'm going to take NS over NP times VP, and that would give me my voltage in my secondary coil. My changing B over changing T, T is the primary, is what induces the voltage in the secondary coil, right? I've got this changing B field in the primary, creates a changing magnetic field in the laminated core, and that's what creates my changing B field creates an induced current, and that current creates my voltage in the secondary. And it works only for AC, and that's because the AC creates this changing B field. If we use DC, we'd have a constant B field and a constant B field, and because even though we have a B field in the loops, it's not changing, so we wouldn't have any current induced here. So it only works with AC. So if we think about a step-up transformer, right, our voltage increases, or it's greater than the primary. And if we have a step down, our Vs is less than the primary. And so, like I said, we can use that equation, but we can also figure out what the current factor is, or the ratio of currents. We can use the conservation of energy, where we can say the power in the primary is equal to the power in the secondary. And we know power, one of the equations for power is IV. So we can substitute IV for the power for both the primary and the secondary. And when we plug that in, we can then solve for the ratio of the current in the secondary to the current in the primary. And we find that the ratio is the same, right? It's NP over NS. It is reversed with respect to these, but this is the same as V. Let's see if we just go back one. Vs over Vp is Ns over Np. So here, if we have, this is going to be Vp over Vs. All right, so if we know the number of coils for either one of these or both of them, or if we know one of these things, then we can figure out the factor here and be able to solve. So if Vs is less than Vp, how does the Is compare to Ip? So if Vs is less than Vp, then this is going to be greater than 1. And if this is greater than 1, then that tells me that Is is going to be greater than Ip, right? I can just use this, the equation of Is related to Vp. So that's how we just use these formulas, use this formula, this formula here to calculate the voltage, and then we can also use the reciprocal here to calculate the current. So the last thing we're going to talk about is self-inductance. So if we have a battery, so we have a battery, and the battery drives this constant current through a solenoid. So a solenoid is really just a coil of wire. And so there's there's 100 loops of wire here that are connected together, right? And the reason we use a solenoid is to use a current to create a magnetic field, because we get a pretty constant magnetic field when we have these loops of wire, a large number of loops of wire together. We get a constant magnetic field, so it's really handy. And it's also useful for educational purposes too. So the battery drives a constant current through the solenoid, and it creates a constant magnetic field. But when we disconnect the battery, right, we're causing the magnetic field to decrease. and our B field is decreasing. And remember what happens in loops of wire when we have a changing B field, we create an induced EMF or an induced current because the solenoid notices, it says, hey, my B field's decreasing because I'm not connected to the battery anymore. And then it creates its own current to try to stop that from happening. So it creates a current, and it's going to create a current in the direction to increase the B field back to what it was before. And so the changing current passing through the coil produces this changing flux, which induces an EMF. And we can calculate this, right? We can quantify what the EMF is through this equation, negative L. So the inductance times the change in the current over the change in time. That's how we can calculate the EMF when we have an inductor. An inductor is like this solenoid here. The inductor, the symbol for a circuit, it looks like this, right? It just looks like coils of wire. A coil of wire using a circuit for the purpose of inductance is called an inductor. We can also use this equation and notice that this is my magnetic flux of a solenoid. This is the equation for the magnetic flux of a solenoid that's plugged in here. And so we could use that if we were, depending on what the problem asked for. If we think about an inductor, we can calculate the potential difference across an inductor. And we might want to compare it to a resistor, right? Whenever we have a resistor where the current is going this way, right, it's going down, then we say that there's a positive side of the resistor and the negative side of the resistor, and we're always dropping voltage across the resistor. So if we go in the direction of the current, we're dropping voltage across the resistor. That's where we subtract, if this was, say, 10 volts here, and let's say we're dropping 5 volts, we would say 10 volts and minus 5 volts, and we would have 5 volts here. So we're always dropping voltage. But in an inductor, we can go either way. So the potential decreases if the current is increasing. So we see here, if the current is increasing, right, my slope is going to be positive. And because we have a negative here, we're going to have a negative potential. And if the current is decreasing, so di dt would be negative, we'd have a negative times a negative, and that would give us a positive, and we would have then a positive potential. So our potential would be increasing if the current's decreasing. And I think that's it for this slide. And the whiteboard problems will be done in the other videos.